In this video, we are going to talk about atomic theory. We'll look at the basic concept of atomic theory. Now, atomic theory is defined as inquisition to the properties of matter. So matter, which is defined as a substance that has mass and occupies space. So what matter is made up of, that is what atomic theory is talking about. Now, we are going to look at how atomic theory developed over the years. We are going to take our journey from 5th century BCE, where atom was first mentioned. Now, in the 5th century BCE, the popular idea at that time was that matter was continuous. So what does this statement mean? If we say matter is continuous, it means that matter is infinitely divisible. That is, you can cut and cut and cut and divide matter infinitely. And that was the main idea that was supported by most philosophers, including Aristotle. But a man called Democritus had a different idea. He had the idea, a philosophical idea, that matter is not continuous. He had the idea that matter is made up of building blocks, which he called atomos. And atomos, we mean indivisible, or it means uncuttable. So the idea that Democritus had was that matter is made up of building blocks or discrete particles called atomos. So science was not developed at that time, and there was no any experimental proof to that. The first experimental proof to that statement that matter is made up of atoms was given by a man called John Dalton. So the first theory about atom was given by John Dalton. And John Dalton has this to say about atom. In John Dalton's atomic theory, he said that all matter is made up of smallest indivisible and indestructible particle called atom. So atom is the smallest, indivisible, and indestructible part of an element. Alright, so that supports the idea that Democritus had, that matter is not continuous. Then also, John Dalton said that atoms of the same element, they are alike in all proportion, and they differ from atoms of other elements. So atoms of the same element are alike in all ways, in all proportion, that is, in chemical properties and physical properties, and they differ from atoms of other elements. Now, there's a clause to that statement, and we're going to get to that in a little bit. Also, John Dalton said this about atoms, that atoms combine to form compound, and when they do so in simple whole ratio. So atoms combine in simple whole ratio. Then lastly, John Dalton said that atoms can neither be created nor destroyed. So those are the main postulates about John Dalton atomic theory, and it was a very good one. Now, I said that some of these statements have some fallacy or clause to them. So let me start with atoms of the same element are alike in all proportion. Now, there is something called isotopy or existence of isotopy, which disputes that. Isotopy is defined as phenomenon in which atoms of the same element have the same atomic number. Atomic number is equal. They have the same atomic number, but different mass number. So same atomic number, but different mass number. So they will have different mass number because they have different neutron number. So that is isotopy. Now, example of isotopy is seen in chlorine. There are mainly two atoms of chlorine. There's an atom of chlorine that has a mass of 35, and there's another atom of chlorine that has a mass of 37. So if John Dalton said that atoms of the same element are alike in all proportion and differ from atoms of the other elements, that would be incorrect totally, because isotopy exists. Atoms of the same elements are not alike in all proportion. So the two atoms of chlorine, they have different mass numbers. So that statement is not totally correct in the light of isotopy. Then he also said that atoms combine in simple hole ratio. Well, in simple inorganic chemistry, that statement might be valid, but in organic chemistry, atoms do combine in large hole ratio. Then also, atoms can either be created nor destroyed, can also be modified, because in nuclear chemistry, through the process of nuclear fusion and nuclear fission, atoms can be created nor destroyed. But John Dalton atomic theory got us started. Now, what John Dalton atomic theory looked like is a solid sphere. All right, so it looked like a solid sphere. It is indivisible, it is indestructible, it does not contain any other particle. It is the smallest bit of particle that you can have. That is the model of atom that was given by John Dalton. And other scientists add modifications to that or improved on that. But that was the first theory about atomic theory. Now, the next scientist that made improvements over John Dalton atomic theory will be J.J. Thomson. Now, J.J. Thomson carried out an experiment called cathode ray tube experiment or discharge tube experiment. And what does that look like? Now, in a discharge tube experiment, what J.J. Thomson did roughly was that he put a gas in this discharge. He put a gas in this discharge tube and then subjected this gas to some condition. And the conditions were a high voltage and low pressure. So note that when a gas is subjected to high voltage and low pressure, what happens is that the gas begins to ionize. So the gas is going to split into its ions. When he did this, he noticed that some rays were coming out of the cathode and were moving towards the anode. So he named those rays cathode rays. So he observed the properties of cathode rays and he saw that these cathode rays matched the properties of electrons that were previously predicted by scientists like Humphrey Davy and Michael Faraday. So we note that cathode rays are electrons. Now, what are the properties of cathode rays that he observed? Number one, he saw that these cathode rays, which I will call electrons or continue to call electrons, they are negatively charged. So they have a charge of negative. They are negatively charged. How did he know that they are negatively charged? He knew that they are negatively charged because these electrons were deflected towards positive pole of electric field or towards the north pole of magnetic field. So because they were deflected towards the positive pole of electric field, it means that they are negatively charged, because you know that opposite charges attract. So cathode rays or electrons are negatively charged. Then also, he noticed that these electrons, they have mechanical effects. That is, when you put a tiny paddle in the path of cathode rays or electrons, they have ability to rotate those tiny mechanical paddle. So they have mechanical effects, that is, they can rotate mechanical paddle, which means that they are particles, all right? They have a mass. So cathode rays, they have charge mass ratio. Now, at this point, I'm going to pause quickly and then introduce Robert Millikan. Now, note that R.A. Millikan, the contribution of R.A. Millikan to atomic theory was that he found the charge on electron. So do not confuse the work of R.A. Millikan with that of J.J. Thomson. J.J. Thomson calculated the charge to mass ratio, but R.A. Millikan calculated the charge on electron using the oil drop experiment. So charge So charge on electron was the work of R. Millikan. So you calculate the charge on electron as negative 1.6 times 10 is power negative 19 coulomb. That's the charge on electron. So because we have the charge to mass ratio and we have the charge on electron, we found that the mass of electron is about 9.1 times 10 is power minus 30 kilogram. But the work of R. Millikan was charge on electron. The work of J.J. Thomson was charge to mass ratio. So, as a way of summarizing, J.J. Thomson discovered electron using discharge tube experiments. He found that they are negative charge, they have mechanical effects. He calculated the charge to mass ratio. But he did more than that. J.J. Thomson also noticed that this electron, they can pass through thin foil of metal. They penetrate thin foil of metal. So what it means is that electrons, they are subatomic particles because they are smaller than atoms. They can pass through thin foil of metals. So they are smaller than atom. They are subatomic particles. That's how we knew that electrons are subatomic particles and atoms are actually divisible. All right, so that's a quick overview of J.J. Thomson model of atom. Now, what does J.J. Thomson model of atom look like? We know that John Dalton model of atom is a solid sphere which is indivisible and indestructible. The model of atom that was given by J.J. Thomson is called plumb pudding because he knew that atoms contain subatomic particles, which are electrons, but most atoms are electrically neutral. So if atom contain negatively charged particles, that is contain electron, for an atom to be electrically neutral, then that means there must be some positive charges also inside it. So he said that an atom is made up of a pudding of positive and negative charges. So that is what it is known as plumb pudding. All right. So an atom contains diffuse particles, diffuse positive and negative charged particles, which is an improvement over John Dalton, which said that there are no subatomic particles. Atoms are indivisible. But when we went to J.J. Thomson, atoms are divisible. Atoms contain subatomic particles, and his own model of atom is plumb pudding. Now, or the next scientist that we should consider is Ernest Rutherford, which gave an improvement over J.J. Thomson. So let's go ahead and go to Ernest Rutherford. Rutherford model of atom is called nuclear model, and then it was the one that gave us idea of the existence of nucleus. His experiment is known as gold foil experiment. Actually, this experiment was carried out by his students Gigan and Mastin. So what did they do? What they did was that they bombarded thin gold foil with alpha particle. So let's say this is a lead block and these are alpha particles. So they were bombarding thin gold foil with alpha particles. What they saw was that most of the alpha particles passed through the thin gold foil, while some were deflected at large angles, and a few, very few, were sent back. Now, what does this mean? To understand the meaning of this, let's picture alpha particles as a piece of stone, just small stone, and let's picture thin gold foil as tissue paper. So let's say this is tissue paper. Now imagine that you were throwing stone at tissue paper and you were able to get the tissue paper to deflect stone or to send back the stone. All right, what would that mean? That would be so shocking. So from this experiment, the conclusion of Rutherford about an atom is that an atom is made up of a large empty space. And at the center of that large empty space is a positively charged dense center where nearly all the mass of the atom is concentrated. And that positively charged dense center, we called it nucleus. So we have the nucleus at the center. In the nucleus, all the mass of the atom is concentrated, and also there's an electron So the electron is revolving around the nucleus. That was the model of atom that was given by Rutherford, and he called it the nuclear model. So his explanation was that those alpha particles that pass through the thin gold foil pass through the large empty space, where those that were deflected or sent back must have hit the nucleus. And because the nucleus is dense and all the mass of the atom is in the nucleus, the nucleus was able to deflect them or send them back. That is the nuclear model of atom given by Ernest Rutherford. And that was a very great improvement over Thomson that had a plumb body. Now, the problem with Rutherford model of atom is this. Rutherford model of atom could not account for the stability of an atom. Stability of an atom. That was the fallacy, or that was the issue with Rutherford model of atom. And what does that mean? Rutherford said that we have the nucleus at the center and electron is revolving around it. If that is true, in light of atomic physics, if you have a charged particle and you accelerate a charged particle that is moving should be losing energy. So if it's losing energy, it means that the path of this electron will not be circular, either it will be spiral. So if the nucleus is here and electron is moving, the electron, because it's losing energy, should be moving spirally, moving this way. And if it's moving spirally, it should collide with the nucleus and the atom should scatter. So Rutherford model of atom could not account for atom stability or the stability of an atom. So his model of atom had some fallacy. The improvement over this was given by a man called Niels Bohr, and Niels Bohr was the one that gave a model of atom that is called planetary model of atom. So let's look at Niels Bohr or Bohr's model of atom. So planetary model of atom was by Niels Bohr. And let me give a quick overview of his own model of atom. What he said was that Rutherford was correct. That is, we have a nucleus at the center, but the position of electron, as was said by Rutherford, was incorrect. Electrons are not found randomly outside the nucleus. Electrons are located in regions known as orbitals. So the first thing I'm going to bring to your notice about Niels Bohr model of atom is that electrons are located in regions known as orbitals. So an orbital is defined as the region of maximum probability of where electrons are located. So electrons are located in orbitals, which are also called energy levels. Then secondly, note that electrons are not located elsewhere apart from their orbitals, and once electrons remain in their orbitals, they do not radiate energy or gain energy in their orbital. So as long as electrons remain in their orbital or their energy level, they don't gain energy or they do not radiate energy in their orbitals. Then also, certain orbitals are allowed. Only certain orbitals are allowed. So what that means is that orbitals are quantized. That is why we talk about quantum numbers. Alright, so certain orbitals are allowed, and then orbitals or electrons are located only in their orbitals. Now if electron now transits from one energy level to another, that is, they move from one orbital to another, then energy can be absorbed or energy can be released. So if an electron moves from a lower orbital to an higher orbital, it absorbs energy. If they move from higher orbital to lower orbital, it radiates energy. So when electron undergo transition, okay, energy is either gained or absorbed, and this gain of energy, absorption of energy, is accompanied by emission of photon in form of spectrum. So Niels Bohr used hydrogen atom as a case study, and he noticed that the spectral lines that were given or that was emitted in an hydrogen atom were given as this. All right, so this is the hydrogen spectrum where you have the Lyman series, Balmer series, and so on. So if an electron transits from any energy level to the first one, the spectral line is known as Lyman series. From any energy level to second energy level is known as Balmer series, and so on and so forth. So the model of atom that we use today is the Niels Bohr model of atom. So when you see electronic configuration of sodium, which has atomic number of 11, written as this or drawn this way, we are showing that 2 electrons are located in the first orbital or first energy level. Then 8 electrons are located in the second energy level, and 1 electron is located in the last energy level. This is the Bohr's model of atom that says that electrons are located only in their orbitals, and when they remain in their orbitals, they do not gain energy or radiate energy.